Hello, everybody. Thanks for coming to Seattle to this Community Pass Summit this year, and this showing up here in this room today. This is part one of a three-part series of learning things about data stored in columns and not data stored in rows like it's normal. So it's my session first, and then there's two more in the same room just right after this in total. They're all independent, but they also all go together. So that's this. I will be talking about basic SQL Server storage engine, Columnstore. My name is Thomas Großer. I'm a database infrastructure architect, meaning I'll build environments that use SQL Server, and usually I get hired by very big data hoarders that need a lot of data stored in a very efficient way, and we're going to talk about this today. Few information about me. There's my email address. The slides will be shared, and you can download them after the conference is over. And problem there. So, one slide looking back at the past before Columnstore, how regular row store tables are stored in SQL Server. So for every row, you have a row header, couple of bytes, not interesting, and then all the columns are stored behind that header. And then for the next row, it's the same thing. If the data is variable length, the length of the row changes. More than one row is stored on a page, and it's on the page, it's not stored in a particular order, even if it's sorted. That's also important. The reason on the page is so stored that it fits as much data in it as possible. So row 4 and row 3 must not be next to each other. There could be differences in between. So the problem with that architecture is it's great if you need to read all the data. But if you don't need all the data, it's a little bit thing, is because to get to column A of row 1, you not just have to read the whole row, you have to read the whole page that row is on. So to read a 4-byte value, you need to read 8 kilobytes off the disk. And that, if you have to do this a couple of billion times, it's a little bit inefficient. And therefore, the concept of a column store was created. Microsoft is by far not the first one implementing it, but now we have it for a while in SQL Server. So what's different in the column store? The column store has the first column, and then all the values for that column are stored together. Yeah? Not in one gigantic piece, but in pieces of roughly 1 million rows at a time. Yeah? And then for column B, the exact same thing. So if I only want to read column A, the data from column B sits on disk and is never touched. Yeah? And so on. And if I have more than this roughly 1 million rows, then it creates just another group of these files. Yeah? In the next session after this, you will hear how this is done with Parquet files. The same thing, just a different way of storing it. But the basic idea is the same. Yeah? So column stores are great if I need all the data from one or more columns, but not all of them, which is normally in a data warehouse a very common scenario, is that I have a very wide fact table and I need 2 or 3 columns out of 50 to satisfy my report and use that. Quick history, Columnstore was first introduced in SQL 2012, so about 12 years ago, and it was, let's call it, unusable. The problem was, the moment you created a clustered index on a regular table, the table became read-only. Not many database systems have read-only data. The idea is that you add new data daily. So to change the data, you have to drop the index, add the data, and then recreate the whole index. I've seen a lot of people play with it, but very few people actually using it in production. 2014, 2 years later, it became updatable. Yeah? And it also, the difference is, the 2012 version was a column store on top of a regular row store. In 2014, the column store became the actual data. So there is no more underlying row store table. In 2016, they also made the Columnstore index that is on top of a regular row store updatable. Basically, 2016 made the 2012 version read-write. 2014 was a complete new version that was read-write to begin with. And in 2016, you could now have, since the Columnstore became its own data, you can now put an index on top of it. I'm not saying that's a good idea. I'm just saying is you can do it. And again, you can jump off a building. It's not a good idea. Yeah. So this. 2017, they added computed columns, sometimes very important, but not a big update. In 2019, very big update. You could finally do create and rebuild online, which is with very big tables, a very good idea, because taking an index offline for several hours just to rebuild it might not be a luxury we still have in every data warehouse. Some it goes, but most of them not. And in SQL 2022, they gave us a feature we can define the order in which the data is physically stored, which we will learn can be very helpful if done correctly. So, what is the goal of this talk? The goal is to show you how to get the most out of a Columnstore index. You can take any table and convert it into a Columnstore. It will most likely succeed. I don't know if there's some crazy thing in it, but like XML or something that might not work, but if it's, basically if it is, you can convert it. Will this make your database faster or slower? I don't know. It's a gamble, it's a coin toss. Yeah? Most likely not. But if you build your Columnstore with a little bit of what I'm talking to you in this hour, then you can make it blazingly fast. I will share already something that I usually have at the very end. So I had to store 3 trillion rows in a table. Trillion, that's the 1,000 billions. The actual data in a row store would have been about half a petabyte thing. That's not something you want in any database. Yeah? Trust me, because the backup costs alone will kill you. But after 6 iterations, and this is the knowledge I'm sharing today, what I learned after doing it 6 times over till I had it right. Yeah, it's not easy when you have no idea what you're doing because you're doing it 5 years ago. Yes. It ended up to be 15 terabytes. And instead of one query taking about a week to come back, we could have most results of most reports in less than 10 minutes. And that is, again, 10 minutes, 1 trillion rows. It's good. And by the way, this was on a 16-core VM. Not on some gigantic machine. Yeah? This is the part I always keep for the end. It was a 16-core virtual machine to do that. So, let's start with the basics. You have an empty Columnstore and you want to put data in. This is where you can do the biggest mistake of all. When you insert data into Columnstore, Columnstore loves one number. Yeah? And that will become your best friend because you have to know that number. It's 1,048,576. Awesome number. If you do some math, it's 1,024 times 1,024. Why that number? Someone at Microsoft randomly picked it. There's no purpose behind it. Someone picked it. Could have been any other number, like 1,000,000, easy to remember. 1,000 times 1,000? No, let's make it an odd number, but it's what it is. So, one of these row groups, like when SQL bunches it together, what it stores in one big blob that goes onto the disk, is the maximum size of this thing is the 1,048,576. If you insert less, it will still work. The problem is, the fewer you insert, the less efficient the data can be retrieved afterwards. Why? Because if I have 2 with, let's say, 500,000 rows in it, that compresses way worse than if I have 1 with 1 million, because it has to create 2 dictionaries and it has to set up everything. Yeah? So the rules are, if you insert less than 102,400 rows, again, an awesomely random number, now it's 1,024 times 100. Yeah? So not 102.4, but this time it is. If you do less than that, the most horrible thing happens. So this is, you insert 1 row, 2 rows, 3 rows, 4 rows. The most horrible thing is, SQL Server says, oops, that's not really for Columnstore. That's way too less data. Let's create a regular table in the background and stuff the data there. And then we can union that to the rest every time we query it, which of course is not efficient at all. If you insert between the 100 and 2,400,000 and the 1 mega rows, I call it mega rows so I don't bother you with that number all the time, then it will do one of these compressed chunks, but it's not going to be as efficient as possible. If you insert exactly that number, that chunk is as efficient as it can be. If you insert more rows, it will build complete chunks all the time, and then one at the end at the remainder with the same rules as before. So if you insert 1,048,577 rows, you get 1 completely full and 1 with just 1 row, which again is not efficient. Yeah? So that's the problem with this here. Don't underestimate that. This can make your index 5, 6, 7 times slower than it has to be if you just insert it randomly when it comes in. If you do it row by row, you're not getting a column store. You're getting a regular table in the background. Until the whole thing cleans up by either an index rebuild or they have a cleanup agent. I've never seen that thing kick in my life, but I have very busy machines, so yeah. So cleanup is done by rebuilding the index, and there's no point. Yeah, on day 1 it's easy. You insert however, and then you rebuild it, it's done. Once you have 3 trillion rows and you do an index rebuild, that's a multiple day operation, so not a good idea. The insert architecture we ended up using looked like this. We have something that creates the data, whatever that is. It's some application, some other database, whatever it is, and that we used the bulk insert API into SQL Server to put it in a row store table. So whenever we had some data ready, usually a couple of 100,000 or a couple of million rows, random number, we put it in a row store table and parked it there. And then we had a SQL agent job that looked at this other table. Hey, do I have enough rows to actually make a good column store out of it? And when we had that, we pumped it in the column store. Yeah? Luckily, we had so much data that usually like every 5 or 6 minutes, we pumped in a couple of million new rows. If you have slower flow, you might have to have some process that before your report start that flushes out everything. In my case, when we started the reports, like creating 10 minutes after midnight, I had all the data from before midnight in because we had so much, but you might have less. Yeah? And this works also pretty good when you have multiple application servers or multiple applications creating the same data. In our case, a lot of this data was logging data that for legal reasons we had to keep. So it came from various sources into the system. Good. So we talked about how to get data in. Let's assume we've made a perfect column store with all the chunks in the right size and everything else. And now we find out, ooh, there's one row that we need to delete. Can we do it? Yes. Should we do it? No. Problem is, no column store on the planet. And this goes for every other product that's out there. Yeah? Be it Yellowbrick, Postgres, click something, click that, click this. Any product that uses column stores cannot delete. It's just nobody has it. Everybody has a trick how to do the deleting. And SQL, since it can do regular tables, a delete is, again, another shadow table in the background where they store which rows need to be deleted. They keep them in the original column store, but every time you now query, they have to join with that table and eliminate the rows that are deleted. So very inefficient. How can you fix it? You guessed it, you have to rebuild the index. So if you can avoid deletion, avoid deletion. That's the only insert that I have to this, yeah? Good. Is there something worse that you can do to the whole system than deleting the data? Yes, you can. It's called updating data. What is an update when you look in your transaction log? It's a delete followed by an insert within the same transaction. So we learned before that if I insert a single row, it goes into an extra table. So now I have everything in my column store, and now I update one row. First, it puts in table number 2 a row in that this one is deleted, and then it puts in table number 3 the new row in. So now we have to join plus union with the other table. That's already an execution plan this big, and we don't want to deal with it. Yeah? So again, do not update. Easy said. If you have to, of course you can, but then have a plan of fixing this by rebuilding the index afterwards, because it's the exact same thing. The only way to fix that mess is to either drop it and recreate it or do an index rebuild. Unfortunately, that's the case. And that's not a bad thing of SQL, that's just the way column stores work. They are not designed to be modified. That's why the version 1 was read-only, because everybody else at the time was basically read-only. So here we go. Selecting data. This is the most fun part, and we will spend a lot of time on this one. Yeah? So when you have regular tables in SQL Server, there's an almost infinite, and Hugo can probably teach you all of them, ways to get to your data, yeah? By indexing and multiple indexes and all great stuff. With Columnstore Index, there's one way to read the data. Read everything. So you need one row. SQL has to read the whole column store, every row that's in there. Yeah? But that's only true in part. Column store can do something called partition elimination. So if you partition your column store, instead of having to read everything in a full scan, they can skip all the partitions they know they don't need to scan. And how do they know is because you partition on something that's in your where clause. So they can figure it out. For example, if you simplest partition by year. And if you have where year equals something in your query, then it only has to go into the partition with that year. That's a simple version, but it makes a lot. So for this, partitioning by date is usually the most natural instinct that you have and most likely thing is. And as far as I've seen in my life, most reports or so have somehow a relation to a date or a time span. So it's always like, okay, give me the data for a whole year instead of the 10 years I have in my data warehouse, or give me the data of 1 week, of 1 day, or something like this. So it's very common. But the advice from me is partition by the most common search criteria that you have, the most whatever it is for your use case. The one thing that's in every where clause, or in 99% of all the where clauses, that's the one you should pick for partitioning. Not because it's easy, but because it will speed things up a lot. Just imagine you have 100 partitions, and the data is distributed roughly evenly between them, and you can eliminate 99 of them. So instead of a terabyte, you just suddenly only have to read 10 gigabytes. 10 gigabytes, you can't even look how fast that goes. A terabyte, you can watch, progress bar. Yeah? So, as this. Yeah? Consider limits. You can only have 12,000 partitions per table. That also goes for column store indexes. Should you ever do 12,000 partitions? No, because doing it. A partition has no size limit.
So for the column index, Columnstore work, do we need to have a million records in one partition?
You don't have to, but of course it's ideal to have columns. This will never be perfect, but if you can, these chunks, the question is, do all the chunks inside a partition have to be the 1,048,576 rows? No, but most of them, or all but one, should have that size. Yeah? You will always have a rounding thing at the end, yeah? But everything else before that should be perfect, to be clear. Things. Yeah? So, 12,000 partitions, not a good idea. If you Google the interwebs, or Bing, sorry, Microsoft Conference, so Bing the interwebs, then you will see that people start complaining about things going fuzzy once you reach about 4,000 partitions. So my recommendation is try to stick with 3,000, then you have a few extra before it gets funky. Yeah? Yeah? But 3,000 partitions might not be needed to do dates. For example, if you do per month, that's only 12 per year. With 3,000, that's about 300 years or 250 years, which might not be what's in your database. So what we found out, it's good. Let's see if we can cramp into that partition key maybe 2 columns. That thing is, and put them into one value. So we created for our use case an compound key or whatever you want, but in one data type, where we used 4 digits for the year, 2 digits for the month, and 4 digits of a number for a product group. Yeah? Did we ever use that in a query? No, we just used it in the where clause because we always selected we want a report for one product group for 1 month or for one product group for 1 year. And this allowed us to divide our pool of data into roughly 3,000 partitions. So when we read it if we needed it for 1 month, we read 1/3,000th of the data. And if we needed it for a year, we read 12 3,000ths of the data. A massive improvement. So petabytes became gigabytes. Yeah? And that's the key away. So step 1 to make it faster, pick the right partition key and experiment with it. Yeah? Look at all the queries that are coming in because I know it's hard, but it is. The second thing, you have to pick the right data types. As I said before, you can take any table and make it a column store. Will it be good? No. Here's the second number that you have to remember. It's a little bit easier to remember. It's 8 bytes or 64-bit. If all your data types within a column store index table are 64-bit or less, this thing will go way faster. It's like on the highway. If everything would be sports cars, the highway would go way faster than when you have these clunky trucks and semi-trucks and things in between. Yeah, it's just the way it goes. Yeah? So everything that takes less than 8 bytes of storage you can use. Big int, float int, binary 1 to 8, character 1 to 8, n character 1 to 4, date time 2, money, small money, date, bunch of them. And usually the stuff you find in a fact table. Yeah? Most financial data, most sales data, most provision data, everything you're in the warehouse usually fits in that category. With one exception, you can't have long strings and you can't have unique identifiers. 2022, they made strings and unique identifiers a little bit faster. They're not as fast as the rest. They optimized a little bit, but just beware. Still the rule, if you can put it in 8 bytes or less. Try to put it in a reference table and just store the ID. Even joining to that reference table might be faster than putting a more than 8-byte value in the column store. Not all the time, but most of the time. The next one is filter pushdown. If your columns is less or equal to 8 bytes, you can push down the filter into the storage engine from the query processor. What's the difference? In a row store, when you need to filter data, it has to read the whole page, find the row, look at the column, and see does it match my filter or not? So no optimization there at all. In Columnstore, it would just pull the column in that it has to push and then go through row by row and see if the filter works. The trick is they can push that down to the engine that stores it, so it only returns to the query processor the rows that actually match the filter. Can this be a super complex filter that has 20 functions that are nested into each other? No. Yeah? But simple things like larger than, smaller than, equal, within, between, stuff like this works just great. Yeah? If you start putting a cosine on top of a square root or something, no. That cannot be pushed down. Yeah? Maybe it could, but nobody wrote the code for it. Yeah? So if you have the simple case, select from a table where some column is between two numbers. In the row store, as I said, it will pull up everything and process everything. In the column store, if it's more than 8 bytes, it will just read the column Y and figure out which rows it needs. But if it's less than 8, it just gets back the rows that match the filter. Yes. Same goes for aggregate pushdown. Most data warehouses, big queries have average, some median thing calculations. Lots of them can again be pushed down, that instead of give me all the rows and now I calculate the average, you can ask the storage engine, just give me the average of that chunk of data that you've stored. Yeah? Again, cannot be something super complex, but as long as it's simple enough, they can push that down. Yeah? The last two, filter push down and things, since it only works on very simple things, are not always happening, but if they're happening, they help you a lot. Again, we started with a lot of data. We used partition elimination to get rid of most of it, and now we're looking only at parts of it, and we don't have to move that data all the way through the engine to filter it and to aggregate it. Yeah? So that's it. That's you get for free. You have to do nothing to get that, except for keep the data types correct. Again, both aggregate and filter pushdown only works on 64-bit at a time, maximum size. Same explanation as on the other page, pretty much exactly the same thing. Row store has to read everything. Column store with big data type has to read the column and process it. Column store with less just returns, the engine returns just the right way. How do they do this? They pre-calculated it and stored it somewhere. That's the trick. They pre-calculated it, stored it, compressed that, and then use it. That's the trick. So, and in most cases, it doesn't take up any space because they can correlate it to the original data and therefore not taking up space. So, aggregate pushdown. Next one. So, partition elimination was great. But what if I have more than one common filter criteria? Wouldn't it be great if I can eliminate more by not looking at it? So, one partition might have hundreds, dozens, millions, billions of these row groups in it. Great if we can find a way to not read all of them. Simple way, assume like an ever-increasing key, the typical things, 1, 2, 3, 4, 5. So the first one we're going to have the numbers 1 to 1 million and something. The next one, more and more. Again, if I have a from to query, it can look up, hey, which data range is in this row group? And literally in the metadata, they have the smallest and the largest value in the row group stored. So they just look in the metadata, hey, is this between 1 and 1 million? Okay, then I have to read it. It's not between 1 and 1 million, I can skip it, because there's no data in it that is relevant to me. So how do you get that? So within a partition, you should sort by your second most search criteria. You already partitioned by the most common one, or most common ones by putting them into a single key. Now you can sort the whole thing so that with the next one. So in our case, what did I do there? Just some value. Yeah. So if you pre-sort that, that changes a little bit of our diagram how the data gets inserted. I didn't want to make it too complex before. We are not actually waiting for 0.04 million rows. We're waiting for about 100 times that. And then we sort within that and insert it correctly. So we get a lot of row group elimination there. Yeah. In SQL 2022, you can define how your column store is sorted. So when you rebuild the index, that sort order is preserved. Before SQL 2022, when you inserted everything nicely sorted, and then you had the brilliant idea of updating a little bit, and you had to rebuild it, the sort was ignored, and it was rebuilt in a random order, basically how it could find it on disk, which in some cases made it actually way worse than dealing with the extra tables for the deleted rows. The next one goes on in Columnstore and why all this was necessary so far and why these small data types are so important. It's called something called batch mode. Batch mode uses a feature that is in CPUs since the first one was MMX in the multimedia extensions. I think we're talking the year 2000 roughly, some in everything. And then this was basically 64-bit vector registers that could handle a couple of 32-bit values at the same time. Nowadays, there are these instructions in the CPU called SIMD, single instruction multiple data. It's basically a 256 or 512-bit register or piece of data where you can say, okay, this is actually 8 floating point numbers. And let's do the following operation on all of them at the same time. Yeah? And you can imagine that is much faster than doing one after the other. And this is why this size limit is here. Every CPU that is currently supported to run SQL Server has 256-bit registers. Some CPUs have 512-bit registers. In SQL 2022, it will use the better one it can find. In 2019 and before, it just used the 256 thing. Even that, an improvement. Just think, a floating point is 8 bytes, 256. That means you can process 4 at a time. Now you can process 8 at a time if you have the 512. If you bought an Intel CPU in the last 10 years, it's 512. It has the 512. If you bought an AMD CPUs in the last 3 months, it has the 512. They had to wait for some patent to expire. So the thing is, good. So what do we have here? The difference is when it runs in batch mode, it can do another optimization. So normally when SQL Server runs a query, it's a pipeline. So the first operator goes to the beginning of the storage instance and says, give me a row. Okay, I apply a filter. Then the next one comes, okay, give me the filtered row, and now I join it with this other table. And then the next one goes, do this. And then they all go back to the beginning and do it again. And if you do this like, you have to put 100 sheets of paper in a filing cabinet. If you run between your desk and the filing cabinet for each sheet of paper, you will be very fit, but it's going to take you a couple of days to do so. Yeah? In batch mode, what happens is SQL grabs a stack of papers in one go and pushes it through the engine to the end. How many rows? Undefined. Right now, it's about 936, so about 900. Why it is that? That is, if you take a 64 kilobyte piece of memory and divide it by 4 times 8 bytes, and that is what how many rows you can squeeze in with the little bit of metadata overhead. Yeah? Will this change in the future? Definitely, and it has no purpose. But if you ever wonder why batch size is 936 right now, because that's what you get when you divide a little bit more than 64 bits in 64 kilobyte memory. That's what it is. Yeah? So Here's what I said about SIMDs in text, and there's a graphic which is nicely provided from Bob Ward, who has a whole like 3-hour presentation on how this works. But it's basically very simple. You see, these are 4 different rows, and you just process them in one go. Yeah? They all need to do the same thing. If I have to add up all the numbers, I can do one loop through all the numbers and add up all, or I divide them in 4 piles and add each one up, and in the end add them up together, which of course is much faster if I can do it in parallel. As I said, 2022 now has 512-bit. So if you see that your batch size is not 936, but roughly half of it, that's actually a good thing, because that means it gets processed twice as fast, but therefore you can only do less rows at a time. Now, instead of dividing it by 4 in parallel, they now do 8 in parallel. That means in 64-bit, less 8 times rows fit in than 4 times rows fit in. It's just simple math. What about data types larger than 8 bytes? Yes, they exist, and you can use them. As long as you don't query them, it's great. So if you just have something stored, if you have something stored that you need like once a year, or you need it just if there's a lawsuit or something that you can like describe, it's a remark field that told you where the data comes from or something. Yeah, it's perfectly fine. As long as you don't query it, it has no influence. And that's the nice thing about the column storage. If a column is not used, whatever that column does is ignored. Yeah? So you can have them as long as you don't query them, or as long as you don't filter on them. If you just need to pull them out because you need them displayed, it's perfectly fine. You just can't filter on it, aggregate on it, or do any manipulations on it, any functions or something. Because the moment you do that, batch mode, by doing a stack of papers in one go instead of sheet, the SQL has to resort to sheet-by-sheet mode. Sheet-by-sheet mode in SQL is still fast. SQL is a good runner. But the whole stack and running at the same time, way faster. I said it before, if you have large data, see if you can put it in another table. For example, we needed to store the SQL statement together with our logging information. The SQL statement ended up in a regular table with a 64-bit integer key on it, and Columnstore just referenced to it because normally we didn't need it. This was just needed if someone wanted to see it, and then it was a single row lookup. Yeah, so, but that was, we got lucky here. It's not always that you have that. Good. Joining with other tables. So far, we only looked at Columnstore table by itself. Because at Columnstore by itself, everything's fine. But we all know if every query would just touch one table, our life as a DBA or query tuner would be super easy. The reality is you join it with everything else in every other database you find on the same server. Yeah? And sometimes you're even crazy and go through linked servers to other servers, and then they go with linked servers back to your server to get to the original data that you missed, that you already have it. Real world example. So we have a column store indicated by multiple colors in the columns. If we want to join with a clustered index key, so I have a table with a clustered index key, and the column store references that thing, and I need to join, you're good to go. It's a green arrow. You can do that. Yeah? The column store can reference the clustered index on the other side. Works just fine. The column store can point to anything that is a regular index. The join will work fine. Because what SQL does, it scans through the column store and then merges the other thing in. Yeah? If you do a column store against a small heap, it will most likely work. The thing is on most likely. It depends. If SQL is unclever, which happens sometimes, the query processor, and it says, oh, both of these things actually have no index, so I decide to join the other way, because SQL can change the order of tables in a join, then it will not work. But if it scans the big one and scans then in lookups the small one, it will still work. Yeah? It will most likely create a hash join, and then all the data from the small table will be in the hash table, and the big one will be scanned through. If it decides to do it the other way around, it will scan through the small table and then try to put the column store into a hash table, which stops the moment you reach the maximum size of your TempDB. It will fill up all the memory, then fill up all your TempDB, and then stop the query. Yeah? I had a server with 8 terabytes. It still filled it up. 8 terabytes TempDB, it still filled it up like nothing if I had tried to query more than a month at a time in a join that made no sense. Yeah? If you go to a big heap, this will happen all the time because you're reading the whole heap and the whole column store in TempDB, and it just fails. Same if you can hit in-memory OLTP tables, very good quick lookup tables if you need them. And the biggest disaster if you have 2 column stores, because it will then create 2 hash tables. So it takes the content of one column store, tries to put it in TempDB, and then the content from the other column store and put it in TempDB, and it's full way faster than before. But very surely before your query returns with a result, unless you have petabytes of TempDB. Because in TempDB, it's a row store and not compressed, while the column store is compressed. So if you read a terabyte in column store, you have multiple terabytes in TempDB, which nobody has and nobody should have. So don't query. The sad part is, if you reference the column store from any of the others, it will just not really work, because then it has to copy the data into the hash table, which ends up in TempDB, which is just not big enough. Where are the limits? Good question. How much data can I put in? There's a question in the back.
Is there an efficient way to have a primary key on the column store data?
The question is there an efficient way of having a primary key on the column store? The answer is no. You can have a primary key on the column store. We tried that. And let me answer this like 2 slides from now when I told you how much we had compression. Yeah? So you get the answer very soon. Yeah? Where are the limits? I don't know yet. I filled 3 trillion rows into a column store, and it works just fine after we did all the tweaking that I showed you. The first time where we put everything just like in a row store table, it failed miserably. Yeah? After all these optimizations, it worked great. Yeah? The largest column store, about 3 trillion rows. That's the number, all the zeros. I wish my bank account would look like this. And it was compressed about 15 terabytes. So the row had 168 bytes that we stored, and it took about 5.5 bytes to actually store it. That's how good column store compression is. For example, if you have sorted data and you have the same date over and over again, it literally needs 0 bytes to store that. It stores the date once and then says, yeah, the rest of the row group has the same date. Or if you have ever increasing numbers, like 1, 2, 3, 4, 5, they don't try to compress that. They do something called delta compression. They say, okay, the difference between the first 2 rows is 1. The difference between the next 2 rows is 1. 1, 1, 1, 1, 1, 1. Oh, I can eliminate all of that data and just put a flag there that says it's an ever increasing from this number till the end. Yeah? So 168 bytes became 5.5 bytes. WinZip tried to do that. Yeah? Not even close. Yeah? But usually tabular data is cheating because it's very repetitive. Yeah? And even if you use date and time, Columnstore is clever enough to figure out that the first half of that column is not changing, but the second half is. Yeah? So for Columnstore, everything is ones and zeros. There's no, when it processes the data, unless it has to do like sum or something, then it has to interpret it. But for the storage case, it's all ones and zeros, and if it finds patterns, it eliminates. Yeah? So that's really good. So, yeah. In row store, this would have been 0.5 petabyte instead of 15 terabytes. That's a big difference in how much you spend for storage and how much you spend for backups. By the way, backups are still compressible. This is the strangest thing of all. If you take a backup of that and compress it, it's not like normal, but it still gets smaller. So there is improvement for column store. things. So now back to the question from before. We tried to put a unique key on it, like a primary key. Worked great. Took a couple of hours to create it. Problem was the primary key took more storage space than the whole rest of the column. So for the one 64-bit value have a key on it, we spent more storage than on the rest of the data, the 168 bytes. So can you do it? Yes. Will it make sense? Most of the time not. If you need it to check your data, great. I would recommend check it in the staging area and make sure only correct data goes into the column store. Next question. Yes.
Try to compress float data and not only long or decimal data?
The question is, can it also compress floating point data? Yes, it can, and it's great at it. It understands how to do that. Yeah, it's not just integer. Floating point compresses as well. Yeah, so if numbers are identical, they get eliminated, and they can do the same delta. Yeah, so if you have like an increase of 0.257 from row to row, it will still recognize that and do the delta. Yeah. So, more limits. Where are the limits? Part 2. It's all about reducing the work. Yeah? You start out with a big pile of data in Columnstore, and the better you inserted it and the better you prepared it to be read, the less of that data. You drop all the columns you don't need. You don't have to look at that part of the storage. You drop all the partitions that you don't need. Yeah? So if you do it cleverly, you are probably reading 1% of 1% of the data. So 1/10,000th of what you actually have to do if you use partitioning with roughly 3,000 partitions, and you have data that also can do row group elimination by having repetitive data and it's sorted by it. And that is what makes Columnstore fast. Yeah? Can you just create a table, make it a column store, and hope it's faster? Yeah, sometimes it is, because by pure random chance, you get these eliminations. The other one thing you can see here is Columnstore makes no sense if your table is small. Just imagine you have a table that has less than 100,000 rows in it. It ends up becoming a shadow table that is a regular table. There's no point. You're just adding a bunch of overhead to the whole thing. If you have only like 1 million rows, yeah, you will probably have one partition and one row group and no eliminations there, so you have to scan that all the time. A table with a clever index might be much faster. You have billions of rows, now we're talking. Yeah? If my table has less than 50 million rows, I would not even think about it. If it has more than 1 billion rows, it's pretty sure a good candidate. Yeah? If it has more than 1-digit billions, yeah, Columnstore. Nothing else will give you the same speed, but with all the work put into it, so it's stored correctly and all that. This is right now, what with current hardware and current experience it is. If you come back in 10 years, we have that talk again, the numbers will have changed. Yeah? Because bigger CPUs, more memory, different storage, everything we learn, it evolves. Yeah? So my tip, what I usually do is when I design things like this, every 2 or 3 years, I have a look. Okay, did we get some new feature that we haven't thought about back then? Is there any white paper or something, a blog post that I read that actually, I haven't thought about that, we could do this as well. Yeah? When you have larger amounts of data that you have to store, you have to stay on the job. It's like when you have a car. You bring it to service every couple of 1,000 miles. That's by design, because things will break otherwise if you don't take care of them. Yeah? And the same thing goes here. Yeah? It's unfortunately not just a feature you turn on and it does everything automatically. Might it become that in the future? Maybe. I don't know if Microsoft's going to invest in that or not. There are definitely floating ideas what you can do, but it's not something that is, let's say, high on anybody's priority list. Because with all the few tricks that we now learned in less than an hour, you can make things very, very efficient. Good. So that's my summary. You can do count, sums, average, min, max. This is all can all be an aggregate push down. You have date and one column that we push together in the partition key, and some other column that we did with row group elimination, and C, where data is random, but we push down the filter. And then we group by D, E, and F, which again is part of the aggregate push down that was in the first row. And all that runs in batch mode. And then instead of waiting 2 or 3 days for a report to come out, it's about 10 minutes. And to scan half a petabyte in 10 minutes on a VM with 16 cores that has virtualized storage behind it is pretty good. I've never did that on a physical box to see how much more you would get out of it, but I would guess about 30–40% more, but not worth it. That's the convenience of virtualization wins there. So this is what it is. It's a practical example, runs every day in a data warehouse in Connecticut, and keeps on adding data. I will submit next year a session on how we archive the data after 1 year, because that's even more tricky, but I don't know if they picked that because that's a very rare thing. Who archives data? Nobody. Everybody hoards it till there's no more storage left. Yes?
When you partition,
Yeah.
can you rebuild the last partition?
Yes.
So that it redoes the row groups only in that one?
Yeah, so the question is, when you have partitioning, can you just rebuild the index in one partition? So like the last partition, when you have a date thing, you fill it up with crappy versions of the data, and then at the end of the day, you do the whole thing rebuilt? Yes, and I've seen that. In practice, that works too. Yeah. Hugo?
So at the start, you showed about inserting, how you have a process that waits until you have enough new rows and
Yeah.
rows loaded. Does that mean that your queries have to be changed to also query that holding area, or do you just accept that you don't include the most recent data in your results?
So we accept that up to a certain time, the data is not correct. This is, as I said, logging data to prove that certain things went the way they should be. So it's a financial institute that needs to prove that everything went the right way and nobody cheated or something else. So we were lucky that as long as the data was there the next day, everybody was happy. If you have to have the data available immediately, then you have to go the way with the rebuilding the last partition every day. So you know that your last partition is trash, and while you query the data of today, it's going to be the worst query, but most likely everything's probably going to be in memory cached, so might not be that bad. But then at the end of the day, you need to have a process to clean that up. Yeah? I would never go the way that I union the two tables together, because that just screams disaster. I don't know. But as far as I know, the query optimizer, that's just confusing because it's two different types of indexes and everything, and it probably spits out a plan that copies everything into a work table first or something. No. Questions? Yes?
Would you include the partition column also in the order key?
No, you don't have to. Because that would actually, so the question is, would you put, when you order it, also the partition? No, you don't have to do that, and it's actually bad. Because you would have to put it first, so it would always be the same within one partition. So it would never be relevant in that partition. So I rather sort just by the second one and don't have that. Yes?
So if we have 20,000 records pushed in the one table, can we use it?
No.
Every day use it?
No. 20,000 rows, Columnstore.
Every day?
Every day, still probably no, unless you have to store like the last 100 years. But 20,000 rows times 30 is 500,000 per day. you get, by the end of the year, you get 150 row groups. If you partition that, you have like 1 or 2 row groups per month. There's no elimination. You're ending up reading all the data all the time. That's what I'm saying. And the data you have is so small that it's inefficiently compressed to begin with. Yeah? So again, Columnstore is for big amounts of data. And with big, I'm not talking about big data, I'm talking just a lot of rows. 20,000 per day might be a lot, but for Columnstore, it's not. Yeah? You can try it, but don't be disappointed if you end up with a solution that is either as fast as what you have right now, or even slower, with a lot of work.
How does truncating by partition differ from just deleting straight out of the column store?
So if you truncate the whole partition, it goes like this, and everything is clean. If you delete everything, Columnstore copies all the data into the behind-the-scenes table and keeps it there till you rebuild the index. So truncate is your friend. Yes?
Did I see that it's very efficient for using grids, unique identifiers?
GUID, since 2022, they put in an optimization. So if you have an Intel CPU and you use GUIDs, you are on a good track. If you use an AMD CPU and use GUIDs, you have to wait for the next AMD CPU that can do that. No, the problem is a GUID is not 64-bit, it's 128 bits. And they've done optimizations in 2022 to handle that because a lot of people have GUIDs because developers love them. And yes, but it's not ideal. It works, but it's not perfect. I assume future generations will have no issue with that. But right now, 2022 on an Intel CPU with the correct instruction set. There's like a 20-page document from Glenn Berry, which CPUs work and which not. Yeah. The expensive ones works, the cheap one less so. More questions? Yes, there.
Several questions.
Ooh.
The first one about was the primary key. So have you faced any deduplication issues without primary key?
Yeah, so the question is, if you don't have a primary key, can you have duplicate data? The answer is yes. Will you ever find it? Probably not. Will your reports be wrong? Probably yes. So very careful when you insert your data. So what we had is we had the constraints on the staging table. So unless I filled the same data twice in the staging table after removing it once, it was pretty safe. Yeah? Could we have run checks afterwards? Probably. Since it was logging data, in our case, we were lucky. If I have the log entry twice, it's better than not having it. I get it if it's financial data, that might be a little bit trickier. Yeah? And again, if regulations require you to prove that there are no duplicates, you have to put the constraint on it. And the constraint means you're putting a regular index on top of it, and you now have 3 or 4 times the data that you need.
Have you tried page compression on the unit on cluster primary key?
Yes, you can do all that, and I think it even does that, but it's still 168 bytes to 5 bytes, and then you need 8 bytes in a B tree. That's just more data per entry than it takes to store the whole row. Just that the leaf node is bigger, and the leaf node is not compressed.
Okay, the second question is about have you faced any kind of like training reasons when you're inserting on 1 million rows?
Yeah.
For example, we faced a lot of dictionary size trimming when we insert a batch of rows, like 1 million rows into our
Yeah.
table, and we expect to be a single compressed row group, but
Yeah.
we face that there are more than 1 compressed row group, even if when we
Yeah.
insert 1 million rows
Yeah.
in a batch, is because there was a dictionary size
Yeah.
training reasons.
Stay away from data types larger than 8 bytes.
No, it was likely on floating numbers because there were random numbers.
Okay.
So there were wasn't compressed
Yeah.
as well. And mostly on the
Yeah.
8 and columns also.
Okay. Yeah.
And another
Yeah.
thing,
Okay.
just wondering if you faced it, like caching data when Columnstore data in the buffer pool.
Yeah.
Is there
what happens is the row group blob is stored in a regular row as a blob. So there's a regular row below it. That regular row has all the metadata for that blob, for that row group blob in it, and that's how it goes. Good. One more question.
We had a scenario some times ago where we did an update and delete a lot of them against the Columnstore index. At the same time, you have like concurrent inserts to this Columnstore.
Yeah.
And it actually ended up you have a lot of data groups.
Yeah.
How can we avoid this?
So don't update and insert in large batches. That's how you avoid the groups. Or at the end of the day, once you're done with the whole workload from the day, rebuild the data thing. There's no way around it. Column stores are not designed to work on small amounts of data. And updates are, unfortunately, even if you update all the rows, internally it's a row-by-row operation. Yeah. Maybe they optimize something in the future. Right now, it's just a bad idea. Okay, so we are at time. I will gladly wait outside and answer all the questions, but we should make room for the next speaker and close this out. Let me show quickly for the recording. Feedback is please important. And thank you very much. Here's my email address one more time, also LinkedIn. And the deck is already shared, but 2 slides are missing. I will upload the complete set as soon as I have internet access.